Now that you've learned how to solve basic related rates problems, we can start to use related rates in situations that are a little bit more real life. So at the end of this lesson, you'll be able to solve problems using the concept of related rates. Okay, in related rates problems, all of the information pretty much that I gave you in the basic problems were already, it was just given to you. It said what dx dt was, said what x was, and you were all set. What we'll have to do in these problems is actually dig out that information for ourselves. So, and if you'd like guidelines on page 142, there are actually some guidelines that you can look at, but hopefully after watching this video, you'll be all set. All right, let's start with an example. Example 4. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the area A of the disturbed water changing? So again, we're talking about, it said 1 foot per second. That's how I know I'm changing things with respect to time. First thing that I'm going to do is just to try to pull out my information. It tells me that the radius r is increasing at a constant rate of 1 foot per second. So that's telling me how fast the radius is changing. So it's actually telling me dr dt because it's how fast the radius is changing with respect to time. And since it's increasing, it will be a positive 1. All right. The next thing it tells me is when the radius is 4 feet. So the next thing I know is that r equals 4. Okay, the next thing it says, at what rate is the area changing? So how fast is A changing with respect to time? So what they're wanting me to find is dA dt. So that's what I'll end up looking for when I'm done. All right, so we've got all this nice information. You'll notice we generally take the derivative next. There's no formula to take the derivative of. So we just have to think of what we're talking about here. We're talking about the area, and then I'm talking about circles. So I am going to assume from then that we're going to use the formula for the area of a circle. So the area of a circle is pi r squared. So now, in order to find dr dt and dA dt, I basically just need to take the derivative. So when I take the derivative of A, I'll get 1, and then I'll get the derivative of the area with respect to time, and then equals. Please keep in mind that pi is a constant, so we'll just pull the 2 out front. So I'll get 2 pi r, and then again, we also have to include dr dt because we're taking the derivative of r with respect to time. Okay, from here we're just now got to plug in what we know. We know that r is equal to 4, and then we know that dr dt is equal to 1. So my dA dt will equal 2 pi times 4 times 1. And so my answer is going to be dA dt equals 8 pi. And I also, on these types of problems, need to include units. If I'm talking about the area and the radius was measured in feet, my area is changing at 8 pi feet squared per, how often is it changing? It said that in the radius was changing per second, so this answer will also be per second. So that would be the rate at which the area is changing. Okay, example 5. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. So I know I'm going to be looking for the rate of change of radius when I'm done. First thing that we want to do again is pull out the information. It says air is being pumped into a spherical balloon at a rate, so I know that that's going to be a derivative, and then it says 4 cubic inches per minute. Cubic inches to me lets me know that that's how fast the volume is changing. So we are going to put dV dt, that's how fast the volume is changing, and it's being pumped into the balloon, so it's going to be a positive 4.5. Okay, it says find the rate of change of the radius, so it wants to know how fast is the radius changing. So we are going to be looking for dr dt, and we know the radius is equal to 2, so we'll put r equals 2. All right, from there we've got all of our information, and I now also notice that they nicely gave me a formula for the volume of a sphere that I can work with. All right, if we're going to find how fast things are changing, we need to find the derivative. The derivative of v would just be 1, and then dV dt to show that I'm taking the derivative with respect to time. Once again, since 4/3 and pi are constants, we can bump the 3 out front. 4/3 times 3 will just be 4 pi r squared, and then again I also have to include dr dt. Now from here we can just plug in what we know. We know that r is equal to 2, and we know that dr dt, we don't know dr dt, but we do know that dV dt is equal to 4.5. So I'm going to have 4.5 equals 4 pi times 2 squared dr dt. And if I simplify that a little bit, I'll get 4.5 equals 2 times 2 squared is 4 times 4 is 16 pi dr dt. So if I'm going to solve that for dr dt, I'll actually divide both sides by 16 pi. So I'll get 4.5 over 16 pi. Okay, you may keep your answer like that, or we could put it into our calculator. If you put it into your calculator, we do need to make sure that we put this whole entire denominator in parentheses, and just make sure that you do that if you decide to do that. And then when we get our final answer, our units will be the radius. The radius is measured in inches, so it will be inches per, what are we talking about here? It says cubic inches per minute, so it will be per minute. So hopefully now you can solve a little bit more of an applied problem using related rates.